So we're looking for a function whose value is equal to its derivative. And not only that, but it needs to be equal to its derivative for all values of x. So what would that graph look like? Well, for a start, it will have to get steeper as x increases, so that as x increases, the rate of change of x increases. But there are lots of curves that satisfy that condition. X squared, x cubed, 2 to the power of x, all do that. But the curve that we're looking for has to have a gradient equal to the value of the function. And it turns out there's only one of those, because that criterion defines the set of points on the curve. At each of these points, the gradient is equal to the function value on the y-axis. And as a byproduct, if the derivative of the curve is equal to the function value, then in reverse, the integral of the curve up to that point must also be equal to the function value, so that, for example, this function value here is equal to the area under the curve up to that point. So the question now becomes, well, which mathematical function will do all this for us? Well, it seems like a promising function might be something like 2 to the power of x. But then, why 2 to the power of x? Why not 5 to the power of x? And in fact, although those functions look promising, they do give a derivative or rate of change that is proportional to the value of the function, but it isn't equal to it. And we really want the derivative to be equal to the value of the function. In other words, we're looking for the blue line, not the red and green ones. Well, if 2 to the x is too shallow and 5 to the x is too steep, maybe there's a value that we can raise to the power of x that will be just right, neither too steep nor too shallow. And it turns out that there is. It's a number greater than 2 and less than 3. It can't be written as a fraction. It starts off 2.71828 and carries on forever. But we don't want to write that down, so we call it e.